The next topic that we're going to discuss are solutions. Now, solutions are any homogeneous mixture. That's what we refer to when we talk about solutions. 9 times out of 10 in this course, we're going to discuss aqueous solutions, something dissolved in water. But again, it could be any homogeneous mixture. An example of that would be, say, dissolving 50 milligrams into 1 liter of water. Now, it turns out that there's to distinguish between the two components or multiple components of a mixture, we'll call the substance that changes state the solute, and the component that remains the same state the solvent. Okay, and also if both components start in the same state, or they're stay in the same state, we'll always refer to the major component of the solvent. The major component of the solvent, and whatever you dissolve into the solvent would be the solute. So there's much more water in this solution, so water is the solvent, sodium chloride is the solute. But if you take a small amount of water and you dissolve it in a larger amount of, say, ethanol, ethanol is your solvent, water is the solute. Okay. Again, these can be any homogeneous solution. It just so happens that, most of the time we refer to and we deal with liquid aqueous solutions. Okay, but a gas and a gas is if it's a homogeneous mixture of solution, air being an example, solids and solids, if it's homogeneous, such as alloys, and again, have many different components in the liquid phase. Any of those would be solutions. Okay, we're going to work with concentration differences and describe concentration, but one of the things that we're going to talk about is why solutions form. And a big reason for that being is, of course, compatible intermolecular forces, or more stable intermolecular forces, lower potential energy. Before that, we should also talk about why things mix or do spontaneous mixing. If you have a sodium chloride solution in a beaker and you have a compartment separating them from pure water, if you remove that barrier, of course, sometime later, the entire container will be uniform concentration and thus homogeneous and a solution. So why does that occur? Well, as we'll talk about much greater detail in general chemistry too, spontaneous mixing comes because of entropy, which is a function that describes the disorder of a system. And because there are more ways to disorder a system than to order it, probability dictates that a system will tend to more disorder as a function of time. And so that's why, of course, spontaneous mixing occurs. Now, whether or not a solution will form, whether something will be soluble or not, depends, of course, on the interactions, the intermolecular forces. Is the solute-solute interaction stronger than the solute-solvent interaction, or is the solvent-solvent interaction stronger than the solvent-solvent interaction? We know those interactions are intermolecular forces, so depending on the strength of those, will determine what interaction is more favorable. If the solute-solvent interaction is greater than the solute-solvent, solvent-solvent, solute-solute interactions, the solutions will form. If they're equal, the solution will still form because of entropy. Entropy will sort of tip the scales, and disorder will tip the scales for the solution to form. Even when the solute-solvent interactions are less than, depending on the disparity, entropy could still push it over the edge to forming. But if the solvent-solvent, solute-solvent interactions are much greater, the solution will not form. Okay, so again, we can use the general rule of like dissolves like. So when you're thinking about dissolving a polar molecule, you're going to want to choose any of the common polar solvents. Okay, those are molecules with permanent dipoles. Non-polar solvents listed here would dissolve your non-polar molecules. So an exercise that we could discuss is determining which of these vitamins are fat-soluble or water-soluble. Fat-soluble refers to the non-polar vitamins that would be kept in your fat, or non-polar with nonpolar molecules, and water-soluble vitamins, of course, would be ones that are polar and would dissolve in aqueous solutions. So when you're taking a look at larger molecules, you want to determine whether or not most of the molecule is polar or most of the molecule is nonpolar. Even some nonpolar molecules can have polar groups. But if the majority of the molecule is nonpolar, it will interact much more strongly with other nonpolar molecules. So vitamin C, we can see that there's a hydroxyl group here, 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 and here. And we know those are all polar hydrogen bonding groups. We have a ketone here, a carbon double bond to an oxygen right there. Or actually that would be an ester because of this oxygen here. But anyways, they are both going to have dipole moments. So this molecule is very polar, vitamin C, and so this one would be water soluble. Over here, we've got two carbonyls, carbons bonded to oxygen, so there might be a slight dipole moment there. But we've got much larger areas that are non-polar. So we can predict that vitamin K3 is a fat-soluble vitamin. Vitamin A has one small polar group over here, a hydroxyl group, but then this huge hydrocarbon non-polar chain, and then another hydrocarbon non-polar ring structure over here. So vitamin A is definitely fat-soluble. Vitamin B5 has a carboxylic acid here, an amine group, NH, nitrogen, also hydrogen bonding carbonyl here, hydroxyl group. So lots of polar groups, and so this one would be water soluble, even though I wanted to write fat soluble for some reason. So this is definitely water soluble. Okay. The next thing we're going to want to discuss is whether or not how temperature affects solution formation. And to discuss that, we actually have to think about the energetic processes that occur when solutions first form. And we can either describe them as exothermic, meaning that there's a net transfer of energy from the solution to the surroundings, or endothermic, a net absorption of energy from the surroundings to the solution. So exothermic solutions would give off energy, heat, when they form. Endothermic would absorb or feel cold when they form. Okay? And it's actually the sum of three processes. It takes energy. If you start out with pure solute and pure water, so say water and salt, it takes energy to separate the solid. So if we start down here on our elevator scale of energy, we're going to have to give this energy to separate it. Comes from surrounding. It also takes some energy to separate the water molecules. But when you mix them, when you mix the solute and solvent, that is a exothermic process, meaning it's going to give off energy. So depending on the difference in energy, you either have a net gain in energy, which you can transfer to the surroundings, or you may need energy, in the case of endothermic process, from the surroundings. So separating the solute, separating the solvent is a much more energetic process than just mixing them. So there's a net loss in energy, so you need to absorb that from the surroundings. So that will determine if the solubility of a compound will increase or decrease as a function of temperature. For exothermic processes, solubility will go down as a function of temperature, so as temperature goes up. For endothermic processes, solubility will go up as temperature goes up. So you can think of these as directly proportional, inversely proportional. So by looking at this graph, we can see that sodium chloride is slightly endothermic, increases as a function of temperature. Sodium sulfate is exothermic, decreases as a function of temperature. Now for gases, there's no difference. gases will have a higher solubility in lower temperatures. If you warm up the soda, the carbon dioxide will leave at a faster rate because it is less soluble. And that has to do with the kinetic energy of the molecules. When they form bubbles or leave the solution, the more kinetic energy they have in higher temperatures, the more likely they are to gain enough energy to overcome any intermolecular forces of attractions with the solvent. There's a simple law to calculate the solubility difference as a function, or actually, let me step back. The solubility of gas is also pressure dependent. Okay, and you know that with opening up a bottle or can of soda. In a closed can that's pressurized, there is a greater solubility of CO2. If you decrease that pressure, solubility goes down, and the CO2 will exit and the solution go to the gas phase. So essentially, you can force the equilibrium position of carbon dioxide into the solid or into the liquid as a function of pressure. And you can calculate the solubility of the gas using Henry's laws constants by measuring the pressure of that gas. And depending on the pressure, they all have different values for Henry's laws constants.